In this video, we're going to talk about kinematics, and kinematics has three different variables that we're going to look at pretty closely. Those three variables are speed, velocity, and acceleration. And the difference between speed versus velocity and acceleration is that a speed is a scalar, and velocity and acceleration, they're both vectors. So what that means is a speed has just a magnitude only, and there's no direction that's associated with it. Whereas velocity and acceleration, they have directions that's associated with them. So if I was going 5 meters per second and I didn't tell you anything else, well, that would just be a speed because I didn't tell you which direction I was going in. And if I wanted to make that 5 meters per second a velocity, then I would just say I was going like 5 meters per second north or 5 meters per second south, and then I've turned that speed into a velocity because I've given it a direction. So right now, let's talk a little bit more about the difference between a speed, velocity, and acceleration in terms of their formulas. So if we look at the formulas for each one of these, this is kind of what they look like. So the speed is the distance divided by time, and velocity is the change in displacement over the change in time. And if you notice that each one of these equations, they have some type of initial plus some type of final, and then we divide by 2. That's because all of these different variables right here, they're the average. So all this is the average speed, the average velocity, this is the average acceleration. So you kind of want to keep that in mind that if we're given the initial acceleration or the initial velocity or initial speed, we just need to find the final corresponding variable that goes with it to find what the average speed, velocity, and acceleration are. So these are the basic formulas that we're going to use in kinematics. And right now, I want to take a little bit closer look at speed and velocity because they're really kind of similar, but they're kind of different in one area. And we're going to talk about that area right now. So let's say that we have a man that runs to a tree and back, and we want to calculate his average speed and his average velocity throughout this trip. Now, because I'm dealing with a velocity, I'm going to put a coordinate system right here, and I'm going to define anything that goes to the right as being positive and anything that goes to the left as negative. So let's start off by saying that when the man gets to about halfway to the tree, that he goes a distance of about 25 meters, and he does that in 5 seconds. So to calculate his speed for this, it would be the distance that he traveled, which is 25 meters, and we divide that by his time it takes him to do it in, which is 5 seconds. Now 25 divided by 5 would just be 5 meters per second. Now for his velocity, well, his velocity is just his displacement, and displacement is his final position minus his initial position. So if this is his initial position, which we can classify as 0 right here, and his final position is 25, then we'll just do 25 minus 0, and then we'll divide that by the time it takes him to do that in, which is 5 seconds. So his displacement is 25 divided by 5, or it's a positive 5 meters per second. So this is the speed and his velocity are both kind of the same, except for the velocity is positive and the speed doesn't have to be positive or negative because the positive or negative just symbolizes a direction in this case. So let's say that the man goes another 25 meters and he gets to the tree, and he does that in 5 seconds again. So to calculate his speed for this case, it would just be his total distance that he traveled, which would be 50 meters, and we would divide that by 10 seconds because that's how long it took him to do it in, and this would be 5 meters per second. Now for his displacement. Well, his displacement, he started here, which was his initial position, and his final position is now over here, which is 50 meters. So this is just going to be 50 minus 0, so his displacement is 50, and the time it takes him to do it in is the same as the speed, which is 10 seconds. So his velocity is positive 5 meters per second. Now let's say that the man, once he gets to the tree, starts to go backwards. And when he goes backwards, he goes first his 25 meters, and he does that in 5 seconds. So this time for his speed, we would just total up his total distance that he traveled. His total distance is going to be 75 meters, and the time it takes him to do it is 15 seconds. So his speed didn't change at all, which is still going to be 5 meters per second. Now for his velocity. Well, his velocity, he started right here, which was initial position, which was 0. And now his final position is right here, which is 25 meters. So we just take this final right here and we subtract it by the 0. So this displacement is 25 meters. And the time it takes from doing it is 15 seconds. So this time his velocity is going to be a positive 1.6 repeating meters per second. Now let's say that the man gets all the way back to where he started from, and when he goes back to where he started from, he goes another 25 meters, and it takes him 5 seconds to do that in. So let's do his speed. His speed is just how far did he travel? Well, he traveled a total distance of 100 meters, and he does that in 20 seconds. So his speed is still just going to be 5 meters per second because it was constant throughout this entire trip. That's why this 5 never changed. And his velocity, well, his initial position was here, which was 0 meters, and his final position right here is still 0 meters. So his displacement is 0 meters, and the time it takes him to get in is the same as his speed, which is going to be 20 seconds. And his velocity will now be 0 meters per second. So now that we have that down, let's look at some more advanced kinematic equations. In this equation right here, we have the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. In this equation, we have pretty much the same variables except for this time right here. And in this equation, we have the final velocity. In this one, we don't have a final velocity. So if we're looking for a time, we're going to use this equation. And if we're looking for a final velocity, or we're given the final velocity, we're going to use this equation right here. So one common mistake that students kind of make on these equations right here is that they forget that velocity and acceleration and displacement are all vectors. So that means that whenever we use these equations, we need to assign a positive or negative value, basically based on the direction that that each component's going in. So if we have a velocity that's going to the right, and we want to assign right as being positive, well then this final velocity right here needs to be a positive. And same thing goes with the acceleration and the displacement. So now let's look at this problem up here, and we'll see how we can use these equations down here. So let's say that we have a car that goes 3 meters per second squared, and the initial velocity is 0 meters per second, or the car is at rest, but it's starting to speed up at a rate of about 3 meters per second squared. And when it gets to this point right here, point A, the car is going 10 meters per second, and it travels some distance x right here, and then it gets to position B, and we don't know the velocity at position B. We need to find that. And we also don't know the displacement, the distance between these 2 points right here, but we know it takes 20 seconds for the car to travel this distance, and the whole time the car is traveling at a constant 3 meters per second squared. So let's first see how we would answer this by using these two formulas. So we need to find this displacement right here, and we're given the time. So let's use this equation first. So we know that the delta x is something that we don't know. So this is going to be our unknown right here. So we have delta x is equal to, and the initial velocity that this delta x is referring to is the initial velocity right here, this 10 meters per second. So this is going to be our initial velocity. So the initial velocity would be 10, and then the time that it takes to travel this displacement, this is what this displacement is referring to. It's not referring to the displacement over here because we don't have the time over here. The time that we're going to use is the time in here. So this is the displacement that we need. So this 10 goes in there, and this 20 will go right there. And then we're going to add that to the acceleration. Now the acceleration we said was constant at 3 meters per second squared, so the acceleration would be 3. And the time it takes, again, we use the time here, we'll also use the time right here too, would be 20, and this time we're going to square it, and then we're going to divide that by 2. And notice that I put a positive number for the initial velocity right here and the acceleration right here. And that's because we're going to define anything that goes to the right as being positive. And I could draw like a coordinate system right here where anything that goes up is positive, anything that goes down is negative, anything that goes to the right is going to be positive, anything that goes to the left is negative. And because everything's going to the right, we're just going to assign everything is going to be a positive value. So let's solve this equation now. So we have the delta x is equal to 200, which was 10 times 20, and then we have 3 times 20 squared divided by 2, which is going to be 600. And so now this delta x right here is going to be equal to 800 meters. So this displacement right in here is 800 meters. So we have 800 meters for this displacement. So now that we solve this, let's see what this final velocity would be right here. So in order to do that, I'm going to use this equation right here because we're looking for this final velocity. So the final velocity right here is our unknown. So we have v final, which is going to be squared, and that's going to be equal to the initial velocity, which the initial would be right here, would be this 10 squared. And we're going to add that to this 2 times the acceleration, which would be 3. And the displacement, which would be right here, this displacement from this initial to this final, would be this displacement that it travels between. So this displacement would be 800, and we know that because that's what we found using this equation right here. So when I solve this out, we would get v final is equal to 100 plus 4800, or 4,800, and this v final we could say would be 4,900 or 4,900. And when we take the square root of this and the square root of this, we would get v final is equal to 70 meters per second. So this is our answer for the final velocity at point B, and the displacement right here would be this, and this would be the displacement.